be to implementation. So next presenter, Dr. Ragab Ragab, he is the president of ICID, who will talk about smart irrigation. Dr. Ragab is well-known scientist. He have he is also principal hydrologist of water resources in United Kingdom Center of Hydrology and in Wallingford. He is the editor of Agricultural Science Journal to Cambridge University. So, and he is the president of International Commission of ICID. So please, Dr. Ragab.
Thank you. Good morning, everyone, or good afternoon. My presentation will be focusing on some smart new technologies, given the water shortage in the Arab regions in particular, and the widening gap between water supply and demand. We have two ways. One is to increase the water use efficiency by using smart technologies, or increasing the water supplies. So given the irrigation takes about 70% of the freshwater resources worldwide, I think irrigation needs more attention. And one of these areas of attention is the estimation of the crop water requirements. Crop water requirements is usually calculated as the amount of water evaporated from the soil and the crops. And when we started by Class A pan measurements, which actually it doesn't include plants, and therefore it was overestimating the crop water requirements. And then we moved on to use the equations, which is based on meteorological data. And the famous one here is the Penman-Montes equation that's based on temperature, net radiation, and also it takes into account the canopy resistance for the crops. And that was actually, the canopy resistance was difficult for so many people to measure or to obtain. Then the FAO produced a simplified version where the canopy resistance was taken away and replaced by an average resistance to evaporation value of 70 seconds per meter. And that actually the only thing that was in Penman-Montes is now simplified, and the equation was simplified to that extent to be used. This equation has been used worldwide and still the most commonly equation used. And a lot of people, they use this equation, and they found, and in the experiments, and you will find that also in journals, that they found 70% of water calculated, crop water requirements calculated by this equation, produce the same yield equivalent to when you irrigate with 100% of the crop water requirements. That actually made us to think about why actually when we apply 70% or 60% of the crop water requirements calculated by these equations, we get the same yield as full irrigation. So we have been working on a project north of Italy, and we used eddy covariance to measure actual evapotranspiration, and also we used scintillometers, which is in the middle here, and also we used Cosmos soil moisture measurements. So the scintillometry, or the scintillometer, is a transmitter and the receiver, as you see in the picture here, and it can go up to 10 kilometer path, and that path here across, you will find the change in the air density, and all those eddies that is created by the evaporation are sensed and measured by the receivers here, and from that we can actually calculate the actual evapotranspiration of a mixed cropping system that could also include trees and the grass and everything in the path, and we can actually run that up to 10 kilometers, or we can use it for a shorter also distance. The other instrument is the eddy covariance, and we measure the flow between these sensors, and all those eddies we calculate the integrated flow across the sensors, and we from that also calculate the actual evapotranspiration, and we can calculate that and we use it as crop water requirements. And when we compared what we obtain from the scintillometers, and the EDICO variance. And you can see here that the reference evapotranspiration ET node, which is the continuous gray line. And also you can see here that the red line and the blue lines are the scintillometers, and the EDICO variance are quite low values compared to the ET node. And if we, or the reference evapotranspiration, and if we look at the ATC or crop evapotranspiration, which is the yellow dots here on the top, you will find actually what we calculate from the Penman-Monteith modified equation, that we overestimate the evapotranspiration as measured by the EDICO variance and scintillometers. And actually, that actual evapotranspiration measured represents like a 50% of what we calculate from the equations. So the equations that we use for calculating the crop water requirements actually exaggerates the amount of irrigation requirements, and therefore we can make saving by considering the actual evapotranspiration rather than the potential, which is calculated. And also looking at these equations we use they are based on meteorological data, and they represent mostly the atmospheric demand for water, not the crop and soil demand for water, and that's the big difference we should keep in mind. The other instrument that we used is something based on the soil moisture calculations. And soil moisture calculations, we did historically soil cores first, and then went to neutral probe. And then because of the radioactive source there, we were advised to use a profile probe, which is free from radioactive source. And then we went to ERT, or electric resistivity to tomography, where we can actually have a transects up to 64 meters. And then we went to Cosmos system. The one we used here, we used it frequently in the remote sensing work to calibrate, and it can give us some picture of the changes in the soil moisture below the ground. And for that reason, you can really wonder the soil cores or point measurements that really is not accurate to represent the heterogeneity of the soil. So here you can see how the soil is heterogeneous here, and point measurements that we take does not really represent the heterogeneity of the system. But when you have a transect like this, then you can see the change in soil moisture depends on stratifications, and also depends on the crop on top of that soil. And then we went to the remote sensing, and we had a problem because remote sensing only measured the soil moisture in the top 10 to 12 centimeters only. And then we came to the Cosmos, and the Cosmos now can give us integrated soil moisture values for 300 to 700 meter radius, and non-invasive, completely passive underground fast neutron. It is like neutron probe, but it doesn't have any radioactive source. And we have in the UK about 52 stations across the UK, and those 52 stations, they produce online data. And here the website, you can actually visit that site, because we use this data to predict the runoff. And we have been looking at the possible use of that Cosmos in terms of irrigation. And you can see here we can get the soil moisture over time as a time series from 30 minutes onwards. And also here you can see how the soil moisture responds very well to the rainfall events. So it is very sensitive instrument. And we converted the soil moisture to soil moisture deficit. And soil moisture deficit here, we actually give it a color code. So if it's green, we don't need to irrigate. If it's amber, it is a slightly stressed soil. And if we have it red, it means the crop is really stressed and you need to irrigate. So this new technology can also be used to determine the soil moisture deficit, which is equivalent to the need for irrigation, and also it gives you the amount that you need to add for irrigation. So these two methods, they can give you an accurate estimation of the crop water requirements, and they can save actually a lot of water. And there are some publications here, and also there was a press release by Wiley about this methodology because it was really something new. The Cosmos now, it has got also a 2D system. You can pull behind a Land Rover and you can make a mapping of the soil moisture in the field. Efficient irrigation systems, we also tried to use a twin drip irrigation lines, and only we use one line to irrigate at a time. So in the left here under B, this is the normal irrigation system where the drip lines irrigate all the time. And here under A, it's that you irrigate only with one drip line at a time. So you irrigate basically half of the root zone, and then you switch the other line off, and then the next irrigation, you irrigate the other line. So you have a wet and a dry alternating cycle. And we used subsurface drip irrigation here, and under 10 to 12 centimeters below the soil surface. And we put the plant in the middle between two drip lines, and we alternate the irrigation, and by this we can actually save a lot of water. In addition, if you are using saline water or treated wastewater, the subsurface drip irrigation is the best to use. And the experiments we did, we have been applying this in 3 crops, tomato and potato and maize, and we were able to save 26% of water compared to the traditional drip irrigation, and the 44% of the water when we use sprinkler irrigation. The other thing that, of course, to use to increase the efficiency of the irrigation system is to use low nozzles under the very close to the surface, so to avoid the wind drift and the losses by wind, and also that's also useful for reducing the evaporation losses. And if you can see here also, when the drops, the nozzles are very close to the ground, it might be useful for poor quality water to use low nozzles closer to the ground for that reason. Using nanotechnology or nano irrigation, nowadays there is a new technology, it's called nano irrigation, using semi-permeable membranes with a continuous flow, and it also appears to be saving a lot of water, and also can be used as under the surface, just maybe about 10 centimeters below the surface. And this is example here from Morocco, but that actually also used in Australia. Models can be also good tools for resources management. And there is a model here I developed myself. It's called SaltMed. It is available at the ICID website, or you can go to Google and you download it. It's a free download. And we have also a special issue about the model, and so many really information about the model. It can also simulate all these processes from evapotranspiration to drainage to leaching and to the yield and rotation. The model can give you the soil moisture distribution, the salinity, and also if you have multiple drip system, it also can give you the yield and the biomass or the dry matter. Also, it can give you an idea about the change in the groundwater level. And if you have a rotation or multiple year cultivation, it will also give you the yield and the dry matter. The model can also be used for climate change impact, to look at the crop water requirements in the future, as well as the length of the growing season. This is here a PhD student who managed to run the SaltMed, and he found by the high emission scenarios, 2095, that the season will be shorter for amaranth crop to 98 days compared to the current 114. So by this you have about 16 days irrigation saving. So the other thing is precision agriculture for efficient resources, and also we use that system in SWAPMed project in Morocco, where we have here sensors in the soil moisture, which sends a message to by transmitter to the server, and the server will actually get the control panel of the irrigation system to irrigate if the soil moisture here would reach a critical or threshold value.
Can you go for a conclusion, please?
Yeah, it's I'm closer to it now. Laser leveling is another thing. Tractors full of gadgets and precisions for leveling and management. Drones is also another thing to look at nitrogen deficit or sufficiency. Water quality can also be monitored by drones. and integrated fish and management. And also here, the drainage of the fish farms can go to irrigate. And the other thing really we are looking for is to have the mobile applications for farmers so they can benefit from. And we developed one here for soils. Dr. Amgad definitely produced one for water as well. And I thank you.
Thank you, Dr. Ragab. Let me go for one of the most